Hello, I'm Parul from India, and I will be presenting. My topic is comparative analysis of simulation techniques. It has many techniques, but I'll compare two techniques, that is scan compression and internal scan. My co-authors or the person who worked with me are Arvind Rajawat and Pooja Jain. Arvind Rajawat from my university and Pooja Jain from the company with which we have worked on. We got tools and everything from. Okay, not taking much of the time. This is the outline of the presentation. First, I'll let you know about some basic terminologies. Then what are those two things that I'm going to compare? What would be the flow, results, conclusions, and I'll show you a bit of references. Now, starting with my presentation. Sorry. I'm so sorry. DFT and its terminology. DFT basically stands for Design for Testability. It is used to make your design more testable by adding by making it more observable and controllable. By observable and controllable, I mean that you can if we don't have TFT, we do not insert anything inside our design. We can only test the design from the outside. We don't have any option to test it internally, like to control its internal nodes. But DFT gives us a feature to add extra circuitry such that we can control its internal nodes. Plus, DFT helps us in saving the time, reducing on-field testing. It also reduces the pattern count. Okay, and DFT insertion starts with RTL only. Like you will have a code of your design that will be synthesized, and on that synthesized netlist, we will insert some circuitry to make it more testable. Now, in my case, we will make scan cells out of sequential circuits. What is a sequential circuit? Uh, for example, a flip-flop. So in this, what we do, we just precede a flip-flop by a mux, as you can see in the diagram in the right. This mux will make this flip-flop as a testable one, and this entire combination is termed as a scan cell. What we are doing is we are preceding a mux before a flip-flop. This mux will allow us to give two inputs to the flip-flop. One is a scan in, another is data in. The data in uh, is for the purpose that the flip-flop will given its functional input through this pin. If we want to test this circuit, we will input via scan in pin, which above one you can see. Now, which input to be given to flip-flop is selected by scan enable signal. That is the select signal of the mux. If scan enable is 0, the flip-flop will act as its functional mode, like for which it is inserted in the design. If scan enable is 1, then it will act as a scan flop or as a testing circuit. And whatever is the input, output will be taken as data out or scan out. These are the same pins. Now, the second thing that comes in the terminology is scan chain. We will make such scan cells from all the flip-flops or maybe partial flip-flops, not all, but some crucial flip-flops of the design. Then this entire circuitry is stitched like the the scan out of preceding flip-flop is connected to the scan in of the succeeding one. Such stitching, we keep on doing such a stitching till we have to like a chain. One whose scan in is at the board level for the input, another whose scan out or the output pin is at the board level, so that we can give some input at the board level, propagate it through the scan chain, and observe it at the output. What do we get? Next, third is a scan operation. Scan operation is the same thing that I have been explaining for a single flop, that we can uh, we can operate the flop in test mode or scan or in functional mode for which it is designed. So in scan operation, we put the flip-flop in a test mode. We give it some test patterns or test vector, whatever you want to call it. Then we propagate it. So whatever the output we observe is basically comprised of scan operation, giving the input to the internal states and observing how they behave. Next, what is internal scan and scan compression? Internal scan, basically when, as I explained earlier, making scan chains out of scan flops, whatever we get, testing from those scan chains or from that, it is internal scan. But see, a device have like 20,000, a basic design have more than 20,000 flip-flops or sequential circuit. So if we test in this way, making a chain and test, so think of the time taken for just a basic design, like 20,000 clock cycles. That's not a good idea. So we can have another type of testing in which we break these scan chain, not actually, but we divide these scan chain with the help of a compressor and decompressor, and make it into smaller. When you can see on the lower right corner that a scan chain is broken into flops of 3 3 3 3 3, and there are a lot of scan chains. So by this way, we can reduce the test time. So in scan compression, basically we are breaking large scan chains into smaller chains and feeding it input or output using compression and decompression. The question that could arrive is why we are using compressor decompressor. That is because at the board level, we have limited number of test pins for test input as well as test output. So using a compressor and decompressor, we are not changing number of inputs at the board or at our output pins, but internally we are dividing the chains. So our purpose of reducing the clock cycle is also served, and we are not adding any overhead or at the pin board level of the test pin. As you can see in the upper right corner, there is a like we only like sorry, in the lower right corner you can see the first picture which have scan inputs, scan outputs in this two chains. So it has two input at the board and two output at the board. When you will see at the last picture of the right corner, you'll see we still have just two inputs and two outputs for the test pin. But in between, the number of chains has increased, like these 3 3 3 3. There are a lot of chains. So think of if it is like 15 flops, and if you are dividing it into 3 3, so you will get 5 flops each chain. So and they all work in parallel. So instead of 15 clock cycles, you can do it in just 3 clock cycles. Just giving you one comparison to think. Now, how do we add this extra circuitry under design for testability? To do that, so firstly we have our design, like we will have our basic design in RTL format. We will have a code in Verilog or VHDL. Then we have a tool, design compiler. In design compiler, first we synthesize to get a netlist. Netlist is nothing but it's just your design with some library specification, like it's a gate level, converting your RTL, this behavioral model, into a gate level model. In that we consider libraries like which technology to use, what are the and or gates, what will be the fan in fan out, everything is there in the library files. So using RTL and library file, design compiler provide us optimized synthesized list. This synthesized list is again um, synthesized taking DFT configuration. What DFT configuration is, it says which kind of test do you want to do. Like I already told you, there are many simulation techniques, scan compression and internal scan is the two I am working on. Other than this, there is wrap-off mode, wrap-off mode. So which one you want to use is in question. So under DFT configuration, we provide which type of testing we want, how many actual test inputs we have, how many chains do we want, or how many flip-flops do we want in one chain. So all these details is given under DFT configuration. Then these two files are given to the tool, again design compiler, which provides us a scan inserted netlist. It's nothing, it's just your normal design or your netlist plus this DFT circuitry embedded in it or integrated in that. Now, what is ATPG and simulation? Since I have been writing in my like my subject is simulation techniques, so what is this actually? ATPG stands for automatic test pattern generation. It is the process of generating test vectors. Like we have inserted DFT, we did our part, but is it working properly or not? How to check? To check that, we have to have some simulation. We have to simulate the design. So how we do that? We use a automatic test pattern generation tool to generate the test patterns and check for and the simulation to simulate them and check the schematic for any errors and everything. So how this process works? First, we generate the patterns, then we simulate them, or patterns. You can say them test pattern, test vectors. They are the same, one and the same. So we generate a test pattern, a test bench, then we simulate them depending on the fault model. Like there could be static fault model where you are just checking that some wire is so the smallest example for staccato is is at some wire or at some point it is stuck at one, like it is somehow connected to a ground. So it will always give zero even if you the logic at that wire comes as one, still it will give zero as output as it is connected grounded. So we'll choose what kind of fault model on which we want to simulate our device on. Then and then there is waveform schematic view in which if there are errors, like what we have expected out of a design is not working like that. So to debug, it's better to view the waveforms and the schematic where the connection faults, as I explained you about the stuck at zero fault. So you can see that output is coming wrongly after performing fault simulation. But how does it come? Where does it come to check that? You can just see the third step in waveform or schematic, that where is the connection fault. And for nowadays, simulation has become an integral part of our design testing, because without simulating, you'll never know it's working correct or not. And at least before the chip is manufactured, it's all happening before it is manufactured or before GDS2 is released. Now there are three phases of simulation also, like load and load, in which we will provide test patterns at the input. So providing the test patterns at the input of the module is loading, and to flush or after observing everything, flushing those patterns out is unloading. Next shift, like I have told you, there is a chain of flip-flops in test mode. We have made a chain. So shifting this test pattern from input to the entire chain is called shifting. And then giving the important primary outputs and observing how the circuit behave is capturing the output, how a circuit behave. Okay. Now how the patterns are generated. First, we have scan inserted netlist, that is our netlist in which GFT configuration has been put. Then then the tool for pattern generation, the tool that we use is Tetramex. So this is the flow for that tool. Flow for every tool is more or less the same, but steps may vary a little with the tool. So in our tool, which is Synopsys Tetramex tool, first what happens is we give them scan inserted netlist, then we read the libraries. We must have some internal IPs or modules, or we have taken some modules from other device designs. So everything that is being used in the design will be read. Then a model will be built. Model, it is a flat model of the design. You can more of think it like a high level hierarchical, you can think it of as a schematic. The design forms a schematic for itself to the tool forms a schematic for itself to run this pattern generation thing. Then we have to set the fault model, like I have already told you. There could be different types of faults: stuck fault, and transient faults, in which we check for timing, wire delays and all. So we will we'll set a fault model. Then there will be some DRCs check first, like our clock is not connected to the input of some flip flop. Like it's a design rule check that there is not some connectivity violations, or there is not some placing violations while doing that, because it's technology dependent, right? We have already fetched some technology file. So we are just checking that we after DFT insertion we are not violating any of them. To During DRC check, another input is SPF, that is still protocol file. It contains the basic information pertaining to the scan chains and the design. If the DRC check is passed, then pattern is generated. This is a snippet of a pattern generation script where you'll give the top of your design. In mine, it is 38417. It's a test bench circuit name, so I just gave this. Then the test mode that I selected is scan compression, the technique we will be working on. And this is for the library files. Now the read netlist part, second one is to read the scan inserted netlist that we have synthesized using DC compiler, sorry, design compiler. This is the part for SPF for DRC check. Now here, the next line is to set fault models, which is stuck at, here we are concentrating on stuck at faults. And then if everything goes right, we'll run the run atbg command for on the tool. It will write the patterns for us. Firstly, it will write the patterns on .still format, then it'll convert it on .v. So the last line is just to write the test events and can create a .v of that. And this is a Verilog format file. Now, so now we have the design, we have test patterns. Time to simulate the design. The simulation comprises like the load unload shift. That was the basic how simulation happens, basic steps. Now what are the actual steps that we run to execute a simulation is, first we compile the code, whatever our test bench is, whatever our design is, scan certain at least we will just compile, we'll look for syntax error or anything in the compilation. If compilation pass, then we elaborate. In elaboration for our test tool, we are making again a build, a flat design, considering of its hierarchy and everything, and seeing if there is some unresolved module within the module, like there is a possibility that we misconnecting certain input to the certain output and it's dangling in somewhere in the design. So elaboration check for all these unresolved device modules also. So basically in our elaboration, we are just building a high level model of the design, which includes test bench as a wrapper. Till now, whenever we elaborate or we build model, we only have the design. But here in elaboration, we will have a test bench also. Next, we will finally we have a design. Sorry, build model of the design. Now that build model will be simulated. Like we will apply the test patterns to that model and check whether the expected output meets the actual output or not. And this checking is termed as simulation. Now, for running a simulation, these are the commands for elaboration. We will give the whatever our test bench name is in this boardlib db dot its name. Then we will have HDL where are some environment variables that we need to set. By environment variables, I mean there could be some combinational delays. We have some certain combinational delay. We will give it certain sequential delay, but these will be fixed throughout. To check timing delays, like for a wire, for a flip-flop, there is another kind of testing, which is called transient testing. But here we are focused on stucket. So we will just give that for a combinational logic, this much will be the delay, and for sequential, this much will be the delay, that minimum delay that we should consider. So here in HDL, where we are just giving, we are setting the environment for simulation. No time check is just for letting the simulator to know that it's a stuck at fault model, or we are checking it. No timing. We are not checking the timing issues or for the delay testing. It's not a delay testing. The switches that primarily we will use for simulating is Tmx parallel. That is, it's just for a debug purpose. We can use Tmx series serial also. In Tmx parallel, what happens if we have a chain of suppose we have a chain of 100 flops, and under Tmx parallels, which we give as 10. So after every 10 flop cycle, like after every 10 flop shift, it will give us one output. Since we are working on software, so we can observe anywhere we want until it's not on a real board. So TMX parallel is just for the software testing part. And here, on a real part, we will use TMX series switch on serial switch only. The second switch is TMX part. TMX part basically, when we generate patterns for 20,000 flip flops only, the patterns that will be generated are above 10K patterns if you are recursively testing, like you are rigorously testing for rigorous testing. So simulating 10,000 patterns is like you will take a lot of time. You're maybe it will take one day. So what we actually practice is, instead of simulating in all the patterns in one go, we divide our patterns in a bunch of smaller patterns, like in a pack of say 100 patterns, and we parallelly just run the simulation for all those 100. So the time taken to run 10,000 patterns is way less than the time taken to run 100 patterns, correct? Sorry, the time taken to run 100 patterns is way less than the time taken for 1,000 patterns. So basically, we are making cutting the patterns into 100. Now, since 10 for 10,000, that means we will have 10 patterns file. So which file to run if you want to manually run if there is some error can be done using Tmax part switch. Whichever number you'll give, that test pattern file will be simulated. You can simulate it separately if you will find some error. If you don't find some error, you can run all of them in parallel, right? So below is this simulation command where you can find the STMax switches. There is STMax USB debug stop mode. It's for master slave configuration. That will get to know when you get to. Okay, now these are my compilation logs. If you compile, like I already told you, it will look for syntax errors and some certain more things. So here, after compiling, it will show zero errors, zero warning if your if your design with test benches compiled successfully. This is your elaboration logs. Here, the test-based elaboration is successful and a snapshot is made. By snapshot, I mean that model of the design. And see if you will see if your elaboration, like there is no unresolved components and whatever you have black box, everything is okay, no functionality is breaking, like in terms of connection no functionality is breaking, then the snapshot or the build model will be formed. Here writing remainder snapshot is what you will be shown as a caution of doing that. No, see, these are the simulation logs. Like here, for one design, there was 85 patterns. So those, sorry, 89 patterns. So all the patterns are simulated with zero mismatches. As I told you, when we maybe I missed, when we generate a pattern, in those patterns we have one more field. For every pattern, there is an expected output. So when we actually run it on the design, what happens? We compare that expected output with the actual output that we have received after running the simulation. If the actual output matches the expected output, then there is zero mismatch. If there is like both of them are not inclined, if both are not the same, then it will show some mismatches, like 5 mismatches or 10 mismatches, however how much they are. So here zero mismatches means simulation is okay, the design that you design, and after adding everything, the functionality that you're doing it right now are all same. Okay, so to do this to do this comparison and to do this investigation, I have used the benchmark circuits. Like I have done this comparison 5 benchmark circuits. So these are the details of those benchmark circuits. So the first three are from SCAS S38584, or the main thing that we should look on is number of flip flops in them. Like for S38584, there are 1,452 flip-flops. S38417, it's 1636. S35932, these are just the standard circuits and it's their name. 1728. And one that I have taken is P19, which is from Faraday's lab, which is 6794, and RISC 957599. So just don't remember the you don't have to remember the exact figure, is giving you an approx number of flip-flops in them, because we will be doing all the things in these flip-flops only. So scan cell per scan chain comparison, for I'm just doing it for one circuit, that is S39417. I will be elaborating the result of one circuit and then I'll show the comparison for all those 5. So for 39417, you can see an internal scan. There is one scan chain is formed which has 1425 scan cells. Scan cells like that thing is done. That flip flop preceded by mux, which these are that's called a scan cell. So there is a they have formed a chain after scan insertion which comprise of 1425 scan cells. Now let's come to scan compression side. On the right, you can see there are a lot of chain listed. So after breaking this single chain, how many chains we get is 107 with each flop with either 15 or 14 scan cells. Number of scan cells can be like stated in the DFT configuration, as I have already told you. So as I have chosen the maximum number of scan cell per chain as 15, so it has breaken it in that format only, like 15 or 14. No, for after simulation, see this is the result after simulation. Not after simulation, after pattern generation, we have a coverage check. So for coverage check, uh, under internal scans, we have simulated 18. We have generated 89 patterns, which give us a coverage of 84.98%. By coverage, I means the number of faults that are detected. Sorry, the number of faults that are that are present and detected. It is the ratio of the detected fault upon present fault. And by fault simulation in scan compression, we have 295 patterns, which give us a coverage of 95.37. Now the patterns difference. Why is the pattern count difference? Because in scan compression we have more chains and we are breaking it, so we need more patterns to test it as compared to internal scan, because now our chains are broken. There would be some more there would be some more circuit inserted, so that the functionality of the flip-flops is not hampered. We have to cope up with the functionality, speed, time. Like we cannot hamper that also of a design, because if its timing, work timing is hampered, then there is no point of making it more testable at the cost of its timing and its functionality and everything. So some extra circuitry is also added during scan compression as well as internal scan insertion. So due to that, their pattern count may vary as they have a little of different circuitry. Now, if we have simulated, we have seen, we have detected the. So if you want to see the waveform, if some way you want to observe something on the waveform, so this is the script. The tool that we used is Simvision. It's a so this is the script to do that. In first, you are creating a .shm which will contain your model. In second one, you are telling them keep what to observe. That is, all the variables, all the hierarchy should be observed, all the memory should be observed, and as well as taken. Like it's in your hand how much deep you want to go in the design. If you have a design with 100 hierarchies, so here you can mention which hierarchy you want to observe in the waveforms and everywhere. That's in your hand. So for every hierarchy you have to create a probe if you want some specific hierarchy to be observed. So it in this script is just for that only, describing how you want the database for the observation. And this is the bsub command to invoke the tool Simvision, and here you will give that .shm file name which stores that database. Now if you want to see the these are the waveforms which are being seen in the tool after invoking it. So here wrapper if refers to internal scan mode. So here wrapper if mode is enabled. So you can see at a time only one test mode simulation technique can be enabled. Here it is scan internal scan. So scan compression mode is 0. Like scan compression simulation part, or you can say compressor or decompressor are transparent here. It's just it will just check as a single chain of 1425 cells for the design we were looking for. here you can see whatever patterns are generated, it gives us a feature to see the pattern count where it is working. You can see the CFI, CTI are CFI is functional input, CTI is test input, CFO is functional output, CTO is test output. Say how they are toggling as per the patterns, inputs, outputs. This is the shift enable pin. That shift that I have told you in the first part, that it will select whether it will be acting on test mode or functional mode. Now let's talk about the results. So in first, I'll just show you the results for 38417 one circuit, as I already mentioned. After that, I'll show you the comparison for all the circuits. And what basically for this one circuit it will have scan cell and scan chain comparison, time coverage comparison, and then area analysis. See, for one circuit 38417, the coverage is for internal scans 85.21%, means these are the percentage of detected and tested faults out of all the faults that our device can think, or all the faults that could happen to our design. While in scan compression it is 95.64%. Quite good. That's good. For scan cell, for number of scan cells per chain that is formed in internal scan is 1425, and for scan compression is 14 or 15 scan cells per chain. The simulation time is 3210775 nanoseconds, which is quite large than we can see in scan compression, that is 148025 nanoseconds. Now, if I give you a number of fault detected here, for internal scan it is 52205, and for scan compression it's 58591, which is again greater than internal scan. Pattern count here for internal scan that you want to check a chain continuity is 89, and for scan compression is 295. Like, pattern count at scan compression part is higher as compared to internal scan to get some coverage. Now this is a scan cell per chain comparison for the entire 5 circuits that I have used for doing this comparison, for doing this research. In this, if I say about 38584, we have a single chain of 915 scan cells for internal scan, or same I have kept the same for smaller designs, 14 to 15 scan cells per chain for scan compression. But for a heavy design like B19 risk, which have like 1000, 6000, 7000 scan flops, to keep it compact and easy to observe, I have just given 79 to 80 cells for B19 and 109 or 110 scan cell per chain for risk. Now here's a catch. Here, if you will see, the division of scan cells per chain is like uniform, 14 or 15, 14 or 15. It's not like one chain is having 10, like we have a maximum threshold of 15, but minimum threshold is 0. So it's not like one chain have just 5, other have 15, for 6. It's because we are parallelly executing them. So if we non-uniformly divide, or if it's not near the threshold value, so it unnecessarily increases our chain. So that's why the tool did devise it or divided it in such a way that both are like all the chains will be at its maximum, at its peak only 14 or 15. Like in case of P19, it will be 79 or 80 mostly. if if in the end, if there is some thing is plus or minus, that will be adjusted somehow, but they will always be reaching to the maximum threshold per chain. Scan cells simulation time. Now this is for time and coverage comparison. See, if you will see for 38417, we have already discussed. If I'll show you in our bigger designs like B19, the coverage for internal scan is 98.91%, and for scan compression is 99.51%. The fault detected under internal scan is 6000743, and in scan compression is 604380. if you will observe in all of them, but one thing that you can definitely observe is the fault detected count is greater for scan comparison as compared to internal scan. Second, coverage, even if it is by 0.79, it is greater for scan compression, as you can see in risk. The coverage for internal scan is 97.01 and coverage for scan compression is 97.80. The pattern count, if you'll see, there is a huge difference in pattern count. As we see, pattern count for internal scan is always less than the scan compression one. Then coming to simulation time, there is a drastic change in simulation time, like the time taken to simulate an internal scan and scan compression. For example, I'll show you. No, last comparison field that we have is area comparison. By area comparison, I am not showing you millimeter square area or centimeter square area increase. By area comparison, I mean how many additional gates are required in the design to do certain type of testing. For internal scan, the internal scan simulation technique will induce less number of extra additional combinational circuit compared to scan compression. The reason behind, for internal scan, we have to make a chain, we have to take care of the timings up and down so that the functional and the testing part are in line. But in scan compression, we have compressor decompressor logics that will also increase some area over it. Along with that, we have to put certain mode logic so that compressor decompressor thing and the entire functionality is in line. So some extra circuitry is added in both the cases. Definitely extra circuitry will be added, but in scan compression it will be definitely more than the internal scan. If you will observe, mostly it lies in, on an average, lies in between 10 to 20% area overhead when we compare with scan compression. And if you see, for example, RISC, the last one, which have the maximum number of flip-flops, the area difference or the component difference was 12.2%. Like in standard compression, 12.2% more components were required. While for P19, which is the second highest design with the maximum number of flip-flop, second highest design in terms of flip-flop, it's 13.6%. So what I can conclude, or I have already shown, give you a gist of conclusion, but still to conclude, uh, the simulation time has reduced drastically from 9% or a lot, from 99%, 95%, 98%, as you can see for its for the device design that I have shown you the entire one by one analysis, that is 38417. The timing reduction due to scan compression is 95.4%. For a larger design like RISC, it is 97%. While the coverage, if we see the coverage increase, it's just 9% for smaller, nearly 9% for smaller devices and 1% for larger devices. So we can summarize it like when we do make an industrial design, it is going to be a big design and optimized as well. So we get not much of a coverage difference between internal scan and scan compression, though scan compression is at a upper end, but it's usually in between 2 to 1% only. And second thing, one thing that you have observed is number of flip-flops in a scan chain. Even for internal scan is less than the number of flip-flops that I have shown in a design. The reason behind that, the tool internally does certain optimization that you have a power to not ask tool not to optimize, but I just let the tool optimize. So when it optimizes, it sees certain flip-flops as a memory flop. And for internal scan and compression, memory flops are not put in the chain, because memory flop, you can send of memory is a sequence of a lot of flip-flops. So instead of reducing our area overhead, it will increase area overhead, it will increase time to test. So it will make it worse than making it best. So we don't test memory under scan. for memory testing, there's some another based architecture which is embedded in the design. So just to let you know that the number of flip-flops that are actually in the design, not all the flip-flops are converted to scan cells. So it's partition scan insertion, we can say. Next is it can be concluded as scan compression effective. Now the final conclusion that we have, scan compression is more effective in terms of coverage, in terms of what I say, in terms of timing it gives the very best results. So it is efficient if you want to reduce the test time, if you want to have better coverage. But the drawback here with scan compression is area and pattern count. To get the same coverage, you have to have greater number of patterns for this, and every pattern have a cost. So the pattern count increase, your cost to test increase, if you'll relate. So depending on what is more important, pattern count, your area, you will choose one of the two techniques. The advantage of scan compression is time and coverage. The advantage of internal scan is lower area, lower pattern count. So here I'd like to sum up. These are the references that I have used. The first one, to know how to get a know-how of what scan methodology is, what DFT is, you can refer to this. Second one is just how scan works. Third is for the tool that I have used to do scan to generate patterns. TestMax DFT user guide. It's about the tool, how to use it, how to work with that. Next is since we are using compressor and decompressor to do scan compression, to get a know-how about it, the fourth and sixth reference can be used. Sixth reference is different type of scan compression techniques that could be used. And fifth one is again for those pattern generation part, theory part. And seventh is for SPF still protocol file, as I have mentioned in one of the slide, that for DRC check, design rule check, we need extra input of still protocol file, which contains some data of our scan, our design, and it also contains some initial patterns to check, which is created at the time of scan insertion. And the last difference is to get the benchmark circuits that I have used in my in this testing or in this research. Thank you. Any questions?